field theory gets a little bit more complicated. So if I'm on a lattice, I have to look at neighbors left, right, up, down, etc. And it's all done by crystallographers. So the simplest two-dimensional lattice is called P4MM in crystallography. You know, check it in Dress of Howard condensed matter book. And the main thing that we're doing now, when we go to higher dimensions, we have strong coupling in both time and space. And that's the opposite limit of traditional way of how people think of field theory is mostly oscillations and weak couplings. So this theory is the strong coupling. We have to take care of symmetry. So if on upper cubic lattice, the symmetry is called a hedral group of order 4 rotations, 4 reflections. Now we are in a general setting, and in one dimension, you know, I can write it very nicely here. So we did temporal cat right now, but there's something called a non-map that they also teach you when you study nonlinear systems in quantum dynamics. It's some ugly map, which is 2x2 nonlinear mapping. If you write it on the lattice, it's beautiful. It just says, I take square of my field, multiply the stretching factor, which Anon calls A, compare it to the neighbors. And if you're field theorists, you realize the first non-trivial field theory, scalar field theory, is called 5-4 theory. This one, field theorists don't like because potential doesn't have a bottom, but this one does. So now we are in field theory. And now when you compute the stability, what happens to the stability is I have to look at my neighbors in one dimension, but locally, it depends on particular solution, what my local stretching factor is. But you can do it. Hill, Lindstedt, Poincaré did it in celestial mechanics. And lots of people do it without realizing they do it.